Hi, folks. Today we're going to talk about fractal geometry. Now, fractal geometry is a bit of an extension of chaos theory. It's the geometry of self-replicating shapes. And so fractal geometry is the geometry of shapes which have self-similarity at different scales, such as geometric shapes, or such geometric shapes are called fractals. While real-world objects such as ferns, snowflakes, and trees exhibit fractal behavior, in math, we usually focus on infinitely complex geometric shapes. These are shapes which might not exist in the real world, but they give us examples on which we can explore things. In developing tools to understand infinitely complex geometries, we can better understand the structures of other seemingly infinitely complex objects. Things like coastlines, or cell structures at a chemical level, or the geometry of the human body, or computer science. I mean, there's a lot of applications of fractal geometry. Really, it's just a question of how can we understand things which are infinitely complex. To begin with, we're going to look at some simple examples. The first one is the Koch snowflake. And so let's start with fractals on a line. Here we see a line. In order to make it into a fractal, we're going to need to create a procedure and then repeatedly apply that procedure. Looking at this, our procedure is going to be we're taking the middle third and we're essentially stretching it into an equilateral triangle, where each of these remaining pieces are the same distance as our middle third. And so we take the middle third of the line segment, replace it with two line segments of equal width to the middle third in the shape of an equilateral triangle. We then iterate this, meaning that we're going to repeatedly apply this operation to every line segment we see. So here's a line segment, we apply that. Here's a line segment, we apply that. And we do it to every single line segment. And then we do it again. And then we do it again. And we can iterate this infinitely. Now, the Koch snowflake is applying this exact fractal to a triangle. And so if we take the three sides of a triangle and on each side, we do this process of removing the middle third and stretching it into an equilateral triangle, and we just do it over and over and over again, we get this geometric object. And so to the right is the geometric object we formed from iterating it once, twice, three, four, five times. Imagine we did it infinitely. It would look more or less like this, just with a little bit finer detail. But this is the Koch snowflake. So let's see if we can figure out some of the characteristics of it. The first is infinite complexity. And so one of the defining characteristics of a fractal is self-similarity. The idea that as you zoom in on an object, we will get scaled versions of the original object. And so if we look here, this might be one side of the Koch snowflake. Well, as you zoom in, you're going to see that exact same shape. And we could continue zooming in infinitely, and we would just repeatedly see this same structure pop up over and over again. This self-similarity creates an infinite complexity to fractals. We can then start asking questions about it, like what's the perimeter of the Koch snowflake? And so suppose that our initial triangle has sides of length 1. Well, what is the perimeter after n iterations? Well, we've actually got that mapped out here, but let's talk it through. And so every time we iterate, we turn one line segment into 4. So the formula for number of line segments after n iterations is going to be n equals 3 times 4 to the n. Each iteration, the side length is reduced by a fraction of 1/3, giving the formula s equals 1/3 to the n. Well, if we want to figure out the total perimeter, we would need to multiply those together. So with n equal to 3 times 4 to the n and s equal to 1/3 to the n, the perimeter at each step is given by 3 times 4 to the n times 1/3 to the n, which can be simplified as 3 times 4/3 to the n. This table to the right shows it for the first few values. And so the perimeter goes from 3 to 4 to 5.33 to 9.11. After 10 iterations, we're already at 53.27 as our perimeter. If we go on to infinity, well, if we let n be infinity, the perimeter is going to be infinite. And so we are going to have this shape which has an infinite perimeter. How do we do math with an infinite perimeter? Well, what happens to the area? Will we have an infinite area? Well, let's figure it out. And so to determine the area of the Koch snowflake, we can think of the total area as the sum of the new area at each iteration. And so suppose the initial area is 1. On the first iteration, we had 3 new triangles. And so looking at this, it'd be 1, 2, 3 new triangles, each with an area of 1/9 of your original triangle. On the second iteration, we're going to introduce 12 new triangles, each with an area of 1/81st of your initial area. If we're looking generally, on the nth iteration, we will add 3 times 4 to the n-1 triangles, and that's what we can get from these, each with an area of 1/9 to the n. So we're going from 1/9 to 1/81st, and then multiply that denominator by 9 again, and so on. This gives a geometric series. And so in general, on the nth iteration, we will add 3 times 4 to the n-1 triangles, each with an area of 1/9 to the n. If we multiply and add all of these, we get the geometric series that the area on the nth iteration is 1 plus 3/4 from k, or the sum from k equals 1 to n of 4/9 to the k. And that's a bit of simplification in there. If we actually evaluate this, we end up getting 1/5 times 8 minus 3 times 4/9 to the n. And so this is the area after n iterations. If we let n go to infinity, well, this term disappears, and we're left with an area of 8/5. And so if we start with an area of 1, our final area is going to be 8/5. Whatever our starting area is, we're going to end up with something which is 8/5 that starting triangle area. That's fun. And so now let's see how we can apply this. And one application is the idea of the coastline problem. When we think of the Koch snowflake, it presents a shape with an infinitely complex perimeter and a finite area. These shapes are more common than we think, and the common example is a coastline. When we measure a coastline, it becomes important to clearly define how we wish to measure it. If you measure it with a yardstick or a 20-mile stick, you will get very different results. And ultimately, it's impossible to measure because at what point is a river or marshland no longer part of the coast? And so we need to come up with some way of measuring it. And really, it boils down to what space is actually usable space. With that, let's go on to another set, another interesting one. This one is the Cantor set. And there's a little bit more computation to the Cantor set, but it's a little bit easier to visualize also. And so consider a line segment. Let's remove the middle third of the line segment, breaking it into 2 line segments. Now let's do that again, and again, and again. And so every time you have a line segment, we are going to remove the middle third. We're going to keep removing the middle third ad infinitum. And so we're going to use it, or we're going to do this for forever and a day. The set we are left with is known as the Cantor set. We can see the beginnings of it over here to the right. It has a number of very weird properties, and we're going to see if we can explore some of them. Some of them are going to take a little bit of math, and so you might have to bear with me, but let's take a look at it. Let's start with the measure of the Cantor set. And so we just did a unit on measure theory, and so what would the measure of the Cantor set be? We're just measuring the length of it. Well, every time we iterate the function, the new length is 2/3 of the prior length. And so after n iterations, not the area, but the length is 2/3 to the n of the starting length. And so that means as we go to infinity, we'll get 2/3 to the infinity, which is going to be something ridiculously small. At that point, it will be a measure 0 set. Yeah. And so we have a measure zero set. The next big question is, are the points even connected? And so let x1 and x2 be any two values on the Cantor set. No matter how close these two values are to one another, there will always be a gap between them. We say that the Cantor set is completely disconnected because no matter where you are, you're always going to find values where they're not part of the Cantor set. If you'd like, here's the proof. Suppose that there was a continuous collection of points between x1 and x2, then the measure of the set would be at least x2 minus x1. But since it has measure zero, it must be disconnected. It is sometimes described as Cantor dust or fractal dust. And so whenever we're talking about fractal dust, we mean it's like the Cantor set. The next one is the weird one, and we're going to need a little bit heavier math for this. Is the Cantor set countable or uncountable? And so in our lesson on measure theory, we discussed how a countable set must have measure zero. In the case of the Cantor set, we have a set with measure zero, which is completely disconnected. Does this mean that it's countable? Well, in order to explain this, we're going to have to talk about a new number system. We're going to have to talk about binary. And so let's talk about binary as a starting point. And so you may be familiar with binary numbers. The idea of binary numbers is it's just a system which is comprised completely of ones and zeros. We use a base 10 system. Binary uses a base 2 system. That means that every time you hit 2, we have to go to the next spot over. And so we'd have 0, 1, 10, 11, 100, 101, 110, 111, 1000, 1001. And we just repeat in this pattern. And so our decimal values can be written in binary form. In binary, different place values represent different powers of 2. And so 101 in a base 2 system would be 1 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0, which would be 4 plus 1, which is 5. So we see 101 is equal to 5. For this one, we have 1 in this position, which would be the 2 to the 5th. Then we have a 2 squared, and then we have a 2 to the 0. And so 2 to the 5th plus 2 squared plus 2 to the 0, this number corresponds to 37. We can do this with a number of others as well. And so here we have 101 plus 11. It ends up being 1,000. And what that represents is 5 plus 3 equals 8. Turns out all of our number theory stuff works for binary as well, because number theory isn't really dependent on what system of numbers we are using. Now we introduced binary so that we can introduce ternary. A ternary system is often used to represent the Cantor set, and it is base 3. And so instead of 0, 1, 0, 0, 1, this one's going to have zeros, ones, and twos. And so counting, we see 0, 1, 2, 10, 11, 12, 20, 21, 22, 100, 101, 102, 110, and so on. And so in this case, we would say that the ones place is 3 to the 0, the tens place is 3 to the first, and the hundreds place would be 3 to the second. And so 121 in base 3 is 1 times 3 squared plus 2 times 3 to the first plus 1 times 3 to the 0. In math, that's going to be 9 plus 6 plus 1. So that is 16 in our standard decimal base. We can see a few others here, but this is the general idea with ternary. It's a base 3 system, and it just counts the same way as binary. It counts the same way as our standard decimal system. What we're going to look at is decimals in ternary, because why not make it a little bit more complicated? In ternary, since every single value is going up by a factor of 3, 0.1 in ternary would be 1/3. 0.2 would be 2/3. 0.01 would be 1/9. And we can continue like this. As we're going further and further out, we're talking about different fractions of our numbers. And so 102 in ternary would be 1/3, and then it would be 0/9 and 2/27. And so 1/3 plus 2/27 would be 11/27. And so I know what you're wondering. Why are we talking about ternary? Well, when we look at the decimal values in ternary, something very interesting happens. And so maybe I'll go back to the image. Every value here on this first iteration is going to be between 0 and 0.1. Everything in the middle is going to be everything from 0.1 to 0.2. And everything over here is going to be everything from 0.2 to, well, 1. If we go to the next row, well, this is going to be everything from 0 to 0.01. And then this would be everything from 0.02 to 0.1. What we're getting rid of at every single step is all of the values which have a 1 in them. And so everything that we got rid of in our first step is everything from 0.1 to 0.2. And so anything that has a 0.1 in it is gone. And so when we think of the Cantor set in every iteration, we remove the center third. In ternary, the first iteration would remove everything from 0.1 to 0.1 bar. Note that we keep 0.1 and 0.2 in the Cantor set. If it helps, 0.1 can actually be thought of as 0.02 bar in ternary. Note, did you know that 0.9 bar is the same as 1? You should try to prove that. On the second iteration, we remove the ternary values from 0.01 to 0.01 bar, and from 0.11 to 0.11 bar. At this point, we will have no numbers which have a 1 in their 10th or their 100th place. If we repeat this, the Cantor set can be defined as the set of all numbers which do not have 1 in their decimals. And so imagine if you want your decimal numbers, think of all the possible decimal numbers and then get rid of all of the decimal numbers which have a 1 somewhere in them. That's what the Cantor set is representing. And so the Cantor set in ternary is the set of all values on 0, 1 which do not have any 1 value in the decimal expansion. And so this means 0.2, 0.02202, and 0.020202 are all in the Cantor set. We also have repeating decimals, though. And so that means that 0.02 bar or 0.202 bar and other repeating decimals with just zeros and twos are also in the Cantor set. But this also means that things like this, and so this would be 20, 200, 2000, 20000, 2, and so on, are also in the Cantor set. Well, the pattern for this last one is actually irrational. What this tells us is that we have rational and irrational values in the Cantor set. And that makes this kind of tricky. Because if we just had rational values, then we would know that this set is going to be countable. And remember, that's what we wanted to try and answer back in the day. Is the Cantor set countable or uncountable? Well, if it has irrational values, it might be uncountable. And in fact, that's the case. The Cantor set is uncountable. We can actually prove this using an isomorphism. And so if we think of all of the numbers in ternary, we can map them to the values in binary. And so just map all of the 2's from ternary into 1's in binary. And so, for example, if you think of 0.202 base 3, well, we can map that to 0.101 base 2. Well, if we are including all of the possible rational and irrational versions of this, of things in binary, which have zeros and ones, that is every single number between 0 and 1. And so the counter set ends up being uncountable. It has the same number of numbers as the real numbers. The counter set is a set which is completely disconnected. It has measure 0, but also has an uncountable number of elements. Well, these characteristics are not unique to the counter set. It provides an example which makes us rethink what it means to be countable, connected, and measurable. I mean, this is a very weird set. The idea that everything is disconnected, it's got measure 0, but it still has an uncountable number of elements, that's very, very weird. We already knew that any countable set of points had measure 0, but now we can see that it's possible to have an uncountable set of points also have 0, or measure 0. And so we use this as a counterexample when we're trying to understand a lot of the structures in measure theory as well as analysis. Let's do one more. Sierpinski's triangle. This is an easier one, a lot less mathy. And so Sierpinski's triangle is a triangle which has some interesting applications. The idea of Sierpinski's triangle is we're going to start with a triangle, and then we're going to remove the center quarter. And so cut the triangle like the Triforce. I had a really hard time trying to describe how we're cutting this. I decided on the Triforce. If you don't know what the Triforce is, look up Zelda. So cut the triangle like the Triforce into 4 equal triangles, and then remove the central triangle, leaving 3 smaller triangles. We then iterate. And so we are going to repeatedly remove this center triangle over and over and over again. The shape we get after we do it an infinite number of times is Sierpinski's triangle. And so Sierpinski's triangle shares many characteristics with the Cantor set and with the Koch snowflake. It is self-similar. Every smaller triangle is itself a Sierpinski triangle. It has infinite perimeter and is completely connected. It has an area of 0. There are points of the shape which are not on the boundary of the shape. And so that's kind of like the Cantor set. It also pops up in really weird and interesting places. And let's see where. Let's start with Pascal's triangle. And so recall Pascal's triangle. Beginning with 1 along the 2 diagonals, subsequent numbers are created by adding the 2 numbers directly above them. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and so on all the way down. What happens if you shade the odd numbers? Well, it turns out if you shade all of the odd numbers on this, you get Sierpinski's triangle. Instead of thinking of the triangle going infinitely inward, it goes infinitely outward as you add more and more rows to Pascal's triangle. But you get Sierpinski's triangle just by looking at Pascal's triangle. It's kind of a weird application. But yeah, Pascal's triangle has a lot of weird patterns related to it. We can also generate it using different shapes, which is kind of weird. And so an interesting property of Sierpinski's triangle is that it can be generated from any object. Consider this example where we start with a fish. And so if you begin with a fish and then you create 3 fish, and then you copy and paste that 3 times, and then copy and paste that 3 times over and over and over again, you get Sierpinski's triangle. It does not matter your starting image. You're always going to get Sierpinski's triangle out of it. Again, kind of a weird thing. We also have variations such as Sierpinski's carpet. The Sierpinski carpet is similar structure, but it definitely has some different properties. And so consider the square and then break it into 9 equal squares and remove the center square. Of the remaining 8 squares, break them into 9 equal squares and remove the center square. Repeat infinitely. What characteristics will this have? That's something I'll leave to you. Will this shape have an area after everything is removed? Will it have a perimeter? What'll the perimeter be? What'll the area be? Well, while you explore that, let's talk more about computer-generated fractals. And so these are some of the most beautiful fractals, and this is why fractal geometry and chaos theory became so popular in the 60s through the 80s. And so one of the challenges with generating fractals is that when done by hand, it can be quite tedious. The Sierpinski triangle drawn to the 10th iteration would involve drawing 59,049 triangles, each with a side length 1,024 times smaller than the original. With the growing availability of computers in the 70s and 80s, we were able to generate fractals for the first time. And some of them were unlike anything anyone had ever seen before. Case in point, this one over here is a multibro. We'll talk about that in a little bit. Some of the earliest ones were the Julia sets, and these date back to the 1920s. And so in the 1920s, mathematician Gaston Julia was exploring what happened when you iterate functions of complex numbers. The sets ended up being very interesting and kind of weird. We can see what they look like here. And this is them being drawn by hand, I think. We'll pretend. The sets ended up being very interesting. While some were connected, others were completely disconnected and closely linked to the Cantor set. Without computers, it was difficult to visualize what led to some of the sets being connected and others being fractal dust. And so depending on your initial conditions, sometimes you would get a graph like this, sometimes you get a graph like this, sometimes you get one like this. What exactly was it that was causing this behavior? We couldn't figure it out. And so we really needed computers in order to figure it out. And that's where the Mandelbrot set comes in. One of the first computer-generated fractals was that of the Mandelbrot set. And so in the late 1970s and early 1980s, a group of mathematicians wanted to better understand relations of the Julia set. They used computers to determine which complex values remained bounded under iteration. The shape they got was the first computer-generated fractal based on the number of steps it takes to escape orbit. And we'll explain that more in our next lesson, I think. But this right here is our first computer-generated fractal. And it is a map of all of the possible Julia sets, which is kind of fun. Other examples from the 80s, well, we have trees and snowflakes and ferns and all of those things. And so in the early 1980s, different rudimentary shapes were created using fractal geometry. These often were shapes from nature, such as trees, ferns, and snowflakes. And the main constraint was just the computer power. We didn't have very strong computers back then. But here's one example of something which is a little bit more complex. Vol Libre in 1980. And so in 1980, a 2-minute video titled Vol Libre was created, which highlighted some of the potential in fractal geometry. This 2-minute short shows a visual of flying through a fractally generated mountain range and landscape. Considering the computer graphics of the time, this was quite advanced. It demonstrated the potential for CGI and video games, which use a tremendous amount of fractal geometry to make things look realistic. This was the first time something like this was done. I mean, a 2-minute video in 1980, which was completely computer generated. It was completely done by fractals. It was unheard of. And if you watch it, it's a little bit weird. And by today's standards, it's nothing great. But for 1980, I mean, we're still talking about very early computing, and this was very advanced. We then have video games and movies. And so today, fractals are used to mimic objects in nature, and it's done quite a bit. Mountain ranges, clouds, trees, rivers, and a variety of other structures can quickly be rendered from just a few equations. The reason they look so realistic is because the iterative process used to make the images resemble the iterative processes of chaos theory, which create the original natural objects. I mean, when you think about how a tree is made, it's an iterative process. When we think about how we are generating a tree on a mountainside, that is a similar iterative process. So this image here is a fractal. It's just one which is made to look like a mountain range. We then have abstract art and artificial intelligence. Those are getting a little bit more modern. So as computers became more powerful, rendering high-quality fractal images became a reality. You can find any number of coffee table books with pictures of pretty fractals, such as this very pretty fractal. Isn't it pretty? The iterative process is also how neural networks and artificial intelligence works. It's all just repeating the same algorithm until something convincing is produced. That's how AI works. In particular, you're taking a matrix and multiplying by a matrix repeatedly until something interesting comes up. Final thoughts. Fractal geometry gave us a few interesting new ways to think about a great many subjects. Dynamics, computer science, geometry, measure theory, biology, and discrete math all utilize fractals in some way. We might not use them on a day-to-day basis, but exploring these structures can give us a better understanding of the world around us. And again, this is a very pretty fractal. Fractals are self-replicating. They have images of themselves hidden within them. And when we start exploring the universe as a whole, we start to see this same self-replication. And it's all tied to dynamics. It's all tied to chaos and aperiodic orbits. These types of images, they all come from just a handful of very simple equations. And when you repeatedly apply a simple equation over and over again, you can get very detailed results. With that, I'll let you get to work exploring where you find fractal geometry in the real world. Good luck, folks.